Welcome to CS110L. I'm Ryan. I'm super excited to be here. I will be co-teaching this with Julio this quarter, and we are super excited to have you. So we'll do some quick introductions. Julio, you want to go first?
Yeah, for sure. So, hello everyone. I'm Julio. I am a junior in CS on the systems track. I'm super interested in operating systems, security, architecture, the whole deal. And I took 110L last year, and that kind of is what got me into like this whole world. That's where I learned Rust for the first time as well. So I didn't know anything about Rust. Took 110L, and then like here we are now. Some cute fun facts about me. I've been jump roping since freshman year. I do miss it from this year, but I still continue. It's been fun vibes. And for this pandemic, I've been really into rhythm games. I never played them before. Started in the pandemic, and that's kind of been my thing. But yeah, super excited for this quarter. Nice to kind of see all of you here.
What are rhythm games?
They're kind of like they're games meant to just like hit like beats to like a rhythm. So there'll be a song and you kind of like click at the right time. So it's
Gotcha.
kind of been it's been my thing. You should try.
Modern DDR.
Indeed.
Yeah. Julio, as you mentioned, took the class last year, and so I'm super excited to have him come back because he knows what it's like to have the student perspective, and he's also a section leader. I don't think you mentioned that. So, yeah, super excited to have you. My name is Ryan. I'm a third year, I think, co-term. Yikes. But my background is kind of in web development. I did web development for a long time before Stanford. But since coming here, I've been trying to focus on security in particular. So this class was kind of my passion project, but I always love to chat about it on the side. So if you ever want to talk about anything web development or security related, or like about internships or companies or whatever, I've worked in a lot of different environments. So would love to chat. I have two cats. They may or may not interrupt lecture at some point. And also got really into pottery in the last year as started at Stanford in the Stanford studio, and then that shut down because of COVID. And so then got a really cheap wheel off of Craigslist and have kind of been making stuff for fun on the side. But yeah, that's me. And I also want to give two quick shout outs. First to Will Crichton, who he's a PhD student at Stanford. You may or may not have taken a class with him in the past. And he helped us a lot in figuring out what to teach, how to teach it, all sorts of things. He gave a lot of really, really helpful feedback. So huge shout out to him. And then also I co-taught this class for the first time last year with Armin, who has since graduated. But Armin made like half of this class. So it would be wrong to not give him a big shout out. And who are you? So I sent out the Google Form survey a little bit too late, but thank you for everyone who was able to fill it out. If you haven't filled it out yet, we still want your responses. So please do that if you get a chance. But from the responses we have about 35 students, about 25 enrolled last I checked, and then we have a bunch of auditors. And most people in like why you're taking this class, most people mentioned Rust. I think Rust seems to be the primary reason for taking this class. But also a few people said that they wanted to learn about like common problems in systems programming because they were thinking about going into the systems track, which we're going to focus on a lot. And yeah, this is pretty much what the class is about, understanding like common safety and robustness pitfalls, and we'll talk all about this in the coming quarter. Most people have not heard anything about Rust before, or maybe have heard like things in passing, but I want to be clear, like this is a class that is geared towards people with no Rust experience. So if you fall into this bullet point, that's great. This is perfect for you. If you do have prior Rust experience, the weeks like 2 to 5 might be a little bit slow for you. We're going to be spending a lot of time talking about just like basic Rust control flow and error handling and the type system and whatnot. And so you may not find that very interesting, but stick around, and I promise you we will have some material that you haven't seen before. So if you haven't joined the Slack yet, you can go to Canvas, and there's a Slack tab on the Canvas where you can join the Slack. It's like a unlisted private Slack, so you won't be able to find it from the Stanford directory. But if you go to Canvas and join through the Slack tab, then you can get on there. And we have a social channel where I would love for everyone to just introduce yourself and give us a fun fact about you that has nothing to do with this class or nothing to do with CS. So yeah, thanks for everyone who filled out the forms, but also head over to Slack and give yourself an introduction. All right, so with all that out of the way, let's talk about why we're here. Why, not like existentially, but why does this class exist? Why did we want to teach this? And why is it a good thing that you're here to learn about this? So I'm going to give some code examples. Here is a little snippet of code that I pulled from the internet. I just Googled convert a string to uppercase in C, and this is the first result that comes up. It turns out that this code is really problematic. Like, you should never ever actually write code like this. If you go to this link that I've linked, by the way, the slides are on the course website. It's cs110l.stanford.edu if you ever need to reference these. But if you click that link, there's nothing on that page that gives you any warning that anything is wrong here and that you should not write code like this in production. But it turns out that this is really bad code. So just to step through what we're doing here, we're allocating a buffer, a character buffer. So we're creating room for 100 characters, a string of length 99 with your null terminator, and then you're printing out a prompt, enter a string. GetS is a function that reads a string from like the terminal. So somebody can type something in, and it will populate this buffer with the string that they've typed in. And then they go through each character that the person entered, and they uppercase it. So they take like the ASCII character code and subtract 32 in order to make it uppercase, and then they print out the string in uppercase. So pretty short. Not a whole lot going on here. Does anybody see why this code might be so broken? And what does that mean? Like, how would that happen? Yeah, actually more than 99 characters, because remember, you needed a null terminator at the end. So just to give you a graphic of what we're talking about here, like, what does it mean to overflow this buffer? Like, okay, sure, I can see that we only have space here for 100 characters. What happens if the user actually enters more than 99? And to talk about this, we have to talk about some stuff from 107. We're not going to be talking about 107 stuff in this class. Like, you don't have to understand assembly a lot in this class. We're honestly not going to talk about it besides right now. But I'll just do a quick refresher. So let's say that we're trying to call some function. So maybe we're in main, and main is trying to call some other function, or actually it turns out that there's another function that calls main that's part of the program loader. But let's say that we're trying to call some function. So in order to call a function, what you do is you push the arguments onto the stack for that function. So these are the parameters that get pushed onto the stack. And then you go and jump to the function. And as part of this call instruction, it pushes a return address onto the stack, so that when the function finishes, you know, okay, I'm done running this function. I should return to after this call instruction. So we know where to go back after the function finishes running. And then we jump over to whatever function. This pushes a base pointer onto the stack. Don't worry about what a base pointer is. It's not actually important here. And then we can like create local variables. We could do whatever we want with this stack frame, but this is kind of the stack frame for the new function. And then once we're done, once we're done running this function, what will happen? So like this function will have some assembly instructions. It'll go do some stuff. When it's finished, it pops the local variables off of the stack, and then it like restores the base pointer. Again, not super relevant here. And then how does it know how to go back to the original function, the calling function? There's a return instruction. And what return does is it pops the return address off the stack, and it goes to that memory address in the text segment. So that, like, if we had some more code in the calling function over here, then we would jump to this instruction and continue on from the calling function. Is this good for everyone so far? Any questions about this so far? Okay, so let's say that we're doing something like that code snippet that I showed you before. So we have our function set up. This is our stack frame and whatnot. You know, we've got the parameters, the return address, the base pointer, and we've got some local variables. In that code that I showed before, they allocated a 100-character buffer to store the string. And so I've kind of drawn that as this dotted line here. And the way that stack memory works is the stack grows down. It's kind of weird. The high addresses are up here, the low addresses are down here. The stack is allocated like kind of at the top. You start from the top, and as you push things onto the stack grows down. It's really weird, but just by convention, this is how it works. But when you have buffers inside of local variables and whatnot, like if we declared a character buffer here like we did in the previous code snippet, you start at the beginning of the buffer, which is the low address. And then as you like increment your pointer, as like you write characters into this buffer, you actually grow upwards. The low address is like the beginning of the buffer, and so when you write stuff further into the buffer, you actually go up in the stack. And so if we wrote like 50 characters into our buffer, we would be using up this memory. And what happens if instead of the user typing in 50 characters, the user types in 500 characters, or a lot more space than we had allocated for that buffer? Because there was no check in that code to make sure that we're not going past the end of the buffer, to make sure that we're not reading more than we have space to store, we can actually end up in a situation where the string that you read from the user goes past the end of the buffer and overwrites this memory in the stack. And now, if you go high enough, you can actually end up returning you can end up overwriting the return address. This return address was supposed to point to the area in the text segment where we were supposed to go after this function's done running. But now it's got garbage memory. But even worse, let's say that the user, instead of typing like reasonable text, like hello world, this is a string, instead of entering that into your program, what if they entered assembly instructions at the beginning? And then they overwrite your stack so that the return address gets overwritten with a pointer to the beginning of the buffer. So let me say that again. Previously, the return address was pointing to the text segment, to the parts where the like callee returns to the caller. Now it's been overwritten with the address of the buffer, and the user has populated this buffer. It's like inputted the string with a bunch of assembly instructions. So now when this function returns, it is going to like remove the local variables. It's going to pop that off the stack. It's going to pop the base pointer off the stack, and it's going to return to the return address, which is going to jump here. So it's actually not going to jump to the text segment anymore. It's going to jump to whatever assembly code the user entered. And this is called remote code execution, where you actually take control of the program. It's not running stuff in the text segment anymore. It's not running the program anymore. It's running like the assembly instructions that you've provided inside of this buffer. This was like super mind-blowing to me the first time that I saw that you could do this. Does anyone have any questions about this? This is like really weird stuff going on here. This is very strange, but it turns out that this is how most viruses work. And in fact, the first virus that we know of on the internet was called the Morris worm, was from 1988. And the Morris worm targeted a program called FingerD, which is a really weird program name. But essentially, like imagine that you're working on a network, like, I don't know, your workplace, it has a bunch of computers on the network. And every person has their own computer. Maybe you see a computer on the network and you want to know who owns this computer. So what you can do is you can send a message to FingerD over the network. FingerD is this program that listens on the network to network requests. And it'll tell you the information about the person who owns that computer, who's running that computer, administering it, or whatever. This might seem weird in today because like there are just so many computers on the network that like you don't really care who is using them. Like my phone's on the network. There could be like a smart power outlet on the network. There could be a webcam on the network. There could be a smart refrigerator on the network. Maybe this doesn't make as much sense today, but this was a common program at the time, this FingerD program. So this is code that is actually from FingerD. And does anyone see anything problematic here? Yeah, that's not good. We're calling getS here, exactly like the last program where we allocated some fixed size buffer. We're reading to that buffer with no limit on how on like how big of an input we actually end up reading. And if this input is coming from somebody else on the network, then we could have one computer send us a FingerD message saying like, hey, who's there? Except it's actually a malicious message that overflows our buffer and takes control of the FingerD program. And this actually happened in 1988. It was some curious grad student from MIT, if I remember correctly, that developed what was called the Morris worm. It was this program that would send these malicious FingerD messages to hijack FingerD processes, and then it would go talk to other computers on the network, and it would spread all over the internet. And he took down a substantial portion of the internet. He actually didn't have any malicious intent. It was kind of just a thought experiment of like, oh, hey, this looks interesting. What happens if I do this? But he got arrested, and bad things happened. He didn't mean to take down the internet, but it turns out that his worm, like, it went and looked for other computers to send FingerD messages to, and it was a little too resource intensive, and computers at the time were not very powerful, and so it actually ended up taking down the computers by accident. And this is from 1988, and you look at this tutorial that I linked to from 2021. This was like the first search result on Google, and it's like, have we learned nothing? Like, what? And I was Googling for this, like looking for bad code examples on the internet to highlight, and I didn't expect that I'd find anything this egregious, but here we are, the top search result on Google. And you might say, okay, well, that's cute, but I know not to call getS now. I'm smarter than that. And I'm not even a professional. Professionals don't make such silly mistakes, right? There is this great paper that I would recommend reading. I think I have it linked somewhere. But if you just Google the title, you'll find it. And they did some really great research, but I just want to highlight a few paragraphs here. So what this paper was aiming to do, the goal was to see, okay, cars these days have a lot more computers. There's computers in, there's sensors everywhere. There's computers in like the entertainment center. There's computers in the engine. There's computers everywhere. Is there a way that we can hack into like every different part of the car? So they actually bought a car, got grant money for that, bought a car, and they were like, okay, let's go through every part of this car that like interfaces with the outside world somehow, and let's see if we can break into it. And I don't remember off the top of my head if they made it into like every single remotely accessible piece, but they broke into like at least 8 different parts of the car. It was really bad. And just to call out some one little attack that they focused on. So it turns out that cars these days have cellular modems in them. Some like high-end cars have entertainment centers that will let you like browse the web or stream music from Spotify or something. Even if your car doesn't have one of those entertainment centers, it almost certainly has a cell phone radio in it so that it can report telemetry to the manufacturer. And if your car gets in a severe crash, then it can summon 911 or things like this. And okay, well, because it's exposed to the cellular network, let's see if we can hack into it. So the car is meant to use this 3G modem, but this paper I think was from 2011 or 2012. It was before 3G was like pervasively available everywhere. And so in addition to having a 3G modem, it also has like an analog audio modem, like when you make phone calls, you're using like an analog signal, and so it has one of those, and it has like you can actually call this car. Like it has a phone number. It's not really exposed, but if you can figure out the phone number, you can actually call the car, and it will convert the sounds that you send over that like voice line into bits and bytes, so that the car can like do this telemetry thing and send data back home. So they had this like Airbiquity AQ Link modem that like converts the analog stuff over your voice line to digital bits so that it can communicate over a voice line. The researchers didn't have access to the software, so they couldn't like read the code and be like, oh, that's wrong. But they did some incredible reverse engineering. Like if you have the time, this is a great paper to check out. And they were able to figure out how it works. So they figured out that the AQ Link code supports what are called packets. Like think of these as messages. It supports messages up to 1024 bytes. You can imagine where this is going. But the code that interfaces with this modem, like the code inside of the car that interfaces with this modem, only allocated a buffer for 100 bytes. Even though it's possible to receive messages up to 1024 bytes, they only allocated the space for 100 bytes. And so you end up with a buffer overflow. And they did some cool work. In the end, they came up with a little audio file that you can just like call up the car on an office phone, put it on speakerphone, and then play this audio file, and it will take over the telemetry model of the car, the telemetry module of the car, and from there you can get to the rest of the car. If you know anything about car systems, everything is very tightly interconnected. If you break into one part of the car, you can break into everything else. And this is kind of ridiculous. By the way, I don't know, they didn't say in the paper what kind of car that they bought, but this is not unique to whatever manufacturer they bought. Like every well-known manufacturer has had serious software problems. A couple have had like prolific remote control vulnerabilities where people like just called up the car and took control of it and like cut the transmission, cut the brakes, cut the engine on the highway. But this kind of stuff is all over the place. Oh, here's the link. So like, that's not great. But I just won't work for a car company. Like car companies, they're not like tech companies, right? They don't hire like the best software engineers, and so I'm going to work somewhere else, and we won't make these kinds of mistakes. And to that, I would give you countless vulnerabilities from very well-known companies with big security budgets that are able to spend a lot of money trying to prevent and find these kinds of mistakes, and it still happens. And this one here was from 3 days ago. This is actually the 7th zero-day vulnerability from Apple in just these 3 past months, in just the last actually, I'm not sure if it's the last year or like this year up until this point. And Apple invests a lot into security. Like if anybody can do this correctly, it's Apple. They spend a lot of time trying to develop tools that help us find these sorts of issues and prevent these sorts of issues. And you're like, well, this is still happening. This is crazy. Most of these sorts of issues, most of these security vulnerabilities are from the kind of mistake that I was just talking about, which is the buffer overflow. If you search buffer overflow on this vulnerability database, you'll be scrolling for a long time. You can see how small my little like scroll bar is here. There's just so many mistakes, and most of these are just silly mistakes. For example, here is some code from Chrome OS. So if you have a Chromebook, this is the operating system that the Chromebook is running, and there was an off by one error. Okay, so they accidentally added 1 when they shouldn't have. Off by 1 error that created a 1 byte buffer overflow. And you're like, that doesn't sound so bad. It's just 1 byte. Like, how can 1 byte be bad? Like in the example I showed, you have to overflow all the way up until the return address, and then that causes problems. But it turns out that these Google researchers from Project Zero, they spent a long time trying to figure out how to exploit this, and then they figured it out, and you could read this blog post if you're interested. It turns out that a 1 byte buffer overflow is enough to get remote code execution. You can actually take control of the program that is running, and in this case, this is the kernel. This is like the operating system, the Chrome OS operating system, and so you have total control of the machine now. Let me take a quick look at the messages. Oh, sorry, there's a lot of messages that I missed. Tesla, what about Tesla? I can't name any off the top of my head. Tesla does have a pretty good security research program, but I have heard of vulnerabilities in Tesla, and they are not immune either. Yeah, as Julio said, these mistakes show up everywhere. Nobody is safe. Yeah, the only secure software is one that never gets written. It's like the roll safe meme, like can't have bugs if you don't write any code. But we got to write code, so we need to figure out how to write it well, and that's really the focus of this class. So a lot of these buffer overflows are just silly mistakes. This was a silly off by one error. You and I have written many off by one errors before. So have engineers at Google, and with catastrophic consequences. Some of them are really, really, really hard to pick up on. So this is a very, very subtle buffer overflow. And this code is from a network service. So it receives a packet of data. A packet is just a message. It receives some message over the network. The packet contains some data and also a field that tells you how much data is there. It tells you the length of that data. So we extract the length of the data. We take the length. And we want to copy the first 128 characters into this buffer. So we use a function called strncopy. You may have heard of strcopy from 107. It's usually a really bad idea to call strcopy. And you'll probably see this on assignment 2 in 110, where you have to copy a string somewhere. Just note to self, don't call strcopy, because strcopy is like getS in that it has no awareness of how large the destination buffer is. GetS has this GetS is fundamentally, like, you should never ever call get. It's never secure anywhere, because you have a buffer. GetS has no idea how big that buffer is, and so it just reads user input. And like, if a user ever types more data than the size of your buffer, then you're going to have a buffer overflow. Strcopy can be used safely, but it is hard to. Strcopy also has no awareness of how big the target buffer is, so you kind of need to verify how big is the string that I'm copying, and like, do I have enough space in my target buffer before I actually do the strcopy? So strncopy is a safer alternative to strcopy, in that you tell it how big your destination buffer is and it will never overflow it. It turns out that strncopy is also banned in a lot of code bases. Strncopy is also, like, somehow they managed to mess it up twice. It's got a lot of problems, but we'll talk about this on Thursday. I'm going to spend a lot of time on Thursday talking about this function. But anyways, I digress. So you have some target buffer that you're trying to copy the data from the packet into, and we're saying only copy up to first we're going to verify that we actually have room in the buffer. So if this packet is small enough to fit in the buffer, then copy those number of bytes over. How can this possibly go wrong? It seems like we've done everything right here. We've checked all the boxes. Turns out this can have a buffer overflow. Yes. So that's not necessarily bad, right? Bytes to copy is a signed integer. Like, it could have a negative value. There's nothing fundamentally wrong with that, except for the fact that strncopy takes an unsigned integer as the third argument. So you look at this and you're like, okay, we have a proper bounds check. We're using strncopy. Like, this looks fine. But it turns out that this is signed and this is unsigned. So in C, you can convert between signed and unsigned without explicitly casting. And the compiler will never warn you that something like this is happening. But if you do this and you have a negative value here, what happens to this value as received by strncopy? Like, let's say we pass -1 here. What happens? What value is strncopy going to see? A big number. It actually sees, like, max int. It's the maximum value that you can supply in an unsigned integer. And so now we can end up with a situation where we send a message that has data that is much larger than 128, and we can just lie about how the length of that data, and we can just lie and send like -1 in this packet.length. And then stir and copy, it passes this bounds check because it's like, okay, -1 is less than 128. It's going to call stir and copy, but it's going to pass -1 casted to an unsigned integer, which is going to be like maxint here, and we will end up overwriting like all of memory. That's bad. Like this will definitely segfault, but you could also craft your input message so that you end up taking control over this program with like remote code execution. It's like, this is so ridiculous. This is so hard. Like you can look at this code, and there's nothing in this code, by the way, that tells you that this is unsigned. You'd have to actually look at the stir and copy code and realize this is unsigned. How do we try to prevent these kinds of problems? It seems like if you go into C and C++ programming naively, you're going to be in for a world of hurt, because there's so many different kinds of mistakes, just tiny little mistakes, that can end up completely wrecking your program and making your program horribly insecure. So what can we actually do about this? This is kind of the topic of the whole class, but let's do some brainstorming. Like, if I asked you to write a tool, to say, I give you a program, and your tool does something with this program and tells me, like, hey, you've got some mistakes here, or like, you have a problem here. What kind of, or maybe not even a tool, maybe this is just a workflow change. Like, what would you do knowing that all these kinds of like weird, crazy problems exist? What would you do to try to combat this? Use Rust. We'll get to Rust very soon, and we'll talk about why Rust prevents some of these problems, because it's not immediately intuitive. But why use Rust? I'm just curious if how you justify that. Okay, we have safe and bounds checked wrappers for everything. So do you want to clarify what that means? Yes. So there would need to be two changes. The first change is you would need to actually store the length of the buffers along with the buffer, because in C, like, there's no such thing as an array. I mean, there is, it's like at compile time, but for most practical purposes, there's no such thing as an array. You just have a pointer to some data, to some place in memory, and then somewhere along the way, you need to make sure that you store the length of that. And usually it's like stored as two separate variables. So in stir and copy, for example, we pass a buffer and we pass the length of the buffer. And some of this other stuff I said before is similar. Like you have a variable that stores a pointer, and you have another variable that stores how much data you can actually use there. And that's bad because that can get out of sync. So like, what happens if you have a pointer to some memory, and actually, this is exactly what happened here. So we had some memory, this buffer Q, I think. I don't remember the code off the top of my head. And some length here that calculates like how much memory is available in there. And we got that calculation wrong. We had an off by one error that said we have more memory than we actually have. So you can have mistakes like that, and really you want like some sort of array type or some sort of buffer type that stores the memory and the length and like can never get that wrong. And then you make functions like stir copy, check that data. So you pass it a buffer with like associated length, and then when it goes to use that buffer, it checks to make sure that like you're doing something reasonable. That alone, those two changes alone, would solve a lot of problems in C and C++. Like if they had just done that, the programs might run a little bit slower, and this is actually the justification for why they didn't do that. The programs would run a little slower because every time you use a buffer, you have to make sure that you're within bounds of the buffer. But modern hardware is fast, and I would gladly take that performance penalty over some safety. So you actually can do things like that, and we'll talk about that on Thursday. what else? Stronger type system. We'll talk about like what a type system is and why that helps on Thursday. That's a really good suggestion. Tell your compiler to emit warnings upgraded to errors to ban implicit casts. That's a great suggestion. So the problem here was that we had a signed integer that we implicitly casted to an unsigned integer. And by default, the compiler will let you do this without any sort of warnings or anything. But the compiler has a bunch of like configurable warnings. You can tell the compiler to ban certain things and ban certain behavior and warn you when you do something bad. And so you can like turn on a bunch of compiler flags. You can test a lot of possible inputs. Sanitize. Okay, so somebody knows all the tools that we're going to be talking about on Thursday. There are really two ways that I think about this. If we want to find and prevent these problems, we can either run the program and observe what it does to try to find problematic behavior, or without running the program, we can look at the code to try to find like problems with the code and things that are wrong with the code without running that. So the first technique is called dynamic analysis, and this is where you run the program, you watch what it does, and you look for problematic behavior. I think you all have run Valgrind in 107, and Valgrind is actually a dynamic analyzer. This is what Valgrind does. Why doesn't Valgrind catch everything? Like, I think most of us have had experience with Valgrind catching some problems. It's kind of hard to interpret the results, but at least in 107, like I wrote a lot of buffer overflows, and Valgrind gave me a lot of errors. And I didn't always know what those errors meant, but it caught the errors. Why doesn't everyone just run Valgrind and problem solved? That's exactly right. If your program is deterministic and it only ever does one thing, you can run Valgrind, and if Valgrind passes clean, you can be sure that your program has no memory issues, because your program only has one behavior, and you check that behavior is fine. But there's almost no useful program that's actually like that. Like a Hello World program is like that. It just prints Hello World. That's the only thing it does. But that's not very helpful. Most programs have input from somewhere. Like a user enters some input on the terminal, or it receives some message over the network, or it reads some file from a database or from the computer or something, and the behavior is based on that. And you can run Valgrind with a particular input, and you can say, okay, I didn't see any problems with this input. But there's no really good way to test all possible inputs. And like with that example that we were talking about here, if you were writing manual tests, you probably wouldn't think to put a negative packet length. That doesn't really make sense. That's not a valid thing to do according to the specification. But according to your program, like it'll actually end up taking that and it'll end up working. And if you didn't think to test this, you wouldn't have found this problem with dynamic analysis. So it's limited in that it can find problems, but only if your program actually exhibits the problematic behavior on the inputs that you use to test. So let's go back to this example from the beginning with getS. If you ran this program under Valgrind, Valgrind would actually be perfectly fine with this, as long as you type something that's less than 99 characters or 99 less, because you're not going to see an overflow. Like if you don't actually overflow this buffer, Valgrind is not going to observe you overflowing the buffer, and it's going to say, oh, okay, everything's fine, life is fine. You would have to actually supply a test input that is really long in order for Valgrind to complain. And this is why dynamic analyzers like Valgrind are often combined with other techniques that try to generate lots of bizarre inputs for your program. There's a technique called fuzzing where you generate like pseudo-random inputs, many inputs, and you just run your program repeatedly until you observe a crash or you observe some like memory violation or something goes wrong. You observe it using a dynamic analyzer, but you have to supply kind of like bizarre inputs to try to come up with, okay, if somebody was trying to attack my program, what might they come up with? Just because your program runs fine with normal inputs doesn't mean that it's always going to run fine. There's a different strategy, which is let's not run the program. Okay, this seems difficult. You can't actually, this cannot give us any guarantees that our code is bug-free. It might say that for the 10 million inputs that I've tried so far, nothing bad happened. But what if like the 10 millionth and one input that you try causes your program to crash? It cannot provide any guarantees that your code is bug-free. So you're like, okay, well, let's set this technique aside. And is there some way that we can look at the code without executing it to guarantee that it's bug-free? So static analysis is where instead of running the program, you just look at the code and try to find problematic parts in the code. This is really easy in simple cases. So for example, with that snippet that I was showing before with getS, you can write a static analyzer that just looks for calls to getS and is like, hey, don't do that. And that's a static analyzer. It's really easy. You could just like do Control F and search for getS. And if you find it, then you raise an error. But it turns out that static analysis has a lot of limitations itself. And it's actually impossible to do in the general case. So I don't know if y'all have heard of the halting problem before. I think I learned about it in 103, which is certainly not required for this class. But the halting problem is, it's kind of this thought experiment where can you write a program that tells me whether my program halts, whether my program exits? If I give you a program, can you tell if it runs forever or if it eventually terminates? It turns out that there's no solution to the halting problem. You cannot tell just from reading a program whether that program will exit or not, whether it will halt or not. And to kind of give you an example, an illustration, here is some ridiculous code that it just creates a bunch of random variables and then does like weird stuff to these variables. And if the variables end up with a specific value, then it exits. And like think about how you would actually tell if this exits. I think you actually probably could solve this algebraically just because I made this with like simple variables and there's not a whole lot going on here, but you could make this a lot more complex such that you couldn't analyze it algebraically. And then you would have to actually run this code in your head. And so if you run like 1,000 iterations of this while loop and you're like, it hasn't halted yet. Well, is it going to halt on the next iteration? Is it going to halt on the 2000th iteration? You have to actually run this like in order to see if it exits. But in doing so, you won't be able to tell if it's like going to exit soon or if this just never exits. Like you're going to be running forever trying to tell if this exits because this program could actually run forever, in which case you're going to be running forever trying to like watch, does this terminate or not? This is not static analysis anymore. Like we're actually running this program trying to see what happens to it. And let's just imagine like I take out this return 0 and I swap it for a segfault. Let's say like I dereference the null pointer. Does this program segfault or not? Like, is this program memory safe? Does it run fine or does it have some problems? You can't actually tell me this without running the entire program, but if you run the entire program, you might actually be running forever. Like, there's no good solution to this. So in the general case, static analysis is impossible to make guarantees. But is there some way that we can simplify this problem? Like, okay, sure, I might not be able to give you a really complicated program like this, but can I give you a more reasonable program? And can you tell me some useful things about it? Can you tell me that, okay, this function is going to be fine. This small function here doesn't have any segfaults, like whatever. Is there some way that we can simplify this problem and still make static analysis helpful? This is going to be what we're focusing on Thursday and the beginning of next week. And this will lead us into Rust because ultimately the goal of Rust is to do some static analysis, is to analyze your program and make sure that you can't write programs that have buffer overflows or use after freeze or all sorts of other memory errors. And we can extend this to other sorts of errors as well. We're just focusing on memory errors at the beginning of this class, but especially in the last half of the class, we'll talk about many other sorts of complex kinds of errors that Rust helps a lot with. So yeah, we'll talk more about this on Thursday, but that is dynamic versus static analysis. Both techniques are very helpful and are used extensively in industry, but they both have limitations, and it's important to understand what those limitations are, so that you can actually say things about your program that make sense. So briefly, some stuff about this class. By the way, this class is listed to go until I think like 150 on Axis or something, but we will be stopping around like 120 every lecture. I don't want to drag this on for super long, so we'll just shoot for 50 minutes. I have a bad tendency to go a little over, but as anyone who has had me in the past knows. But just really briefly, so what is this class about? It's really about like how do we prevent and find common mistakes in systems programming. We're talking about memory safety right now, but we'll be talking about other kinds of errors as well. This is actually not a Rust class. So I know a lot of people mentioned in the survey that you're taking this class because you want to learn Rust. Almost all of our programming will be done in Rust. Like all of the assignments except for one are in Rust. And so you will learn Rust and get some basic exposure to Rust, but the focus is really on like how do we prevent mistakes in general, and less so about like the fancy features of Rust, because there are just way too many for us to cover in a quarter. Rust is a very complex and sophisticated language, and I do not have the experience to do it justice. So some things we'll talk about are listed there. The code requisite is 110. If you've taken 110 in the past, that's totally fine. Don't worry about that. If you're taking 110 this quarter, then that's perfect. You're in the right place. A couple people have asked about 111, and obviously it's a new class that's being taught this quarter, so I'm not 100% sure how their schedule will end up panning out, but I did look at the syllabus and I think you'll be fine. The first like half of this class is actually going to be drawing from like 107 level experience. We're focusing mostly on memory safety, which is something that you had to think about in 107. So you'll be fine for sure for the first half of the class. Then we talk a little bit about multiprocessing, which 110 covers. I'm not 100% sure whether 111 covers it or like to what depth. We don't cover it in a lot of depth, so I think you'll be fine. But there's a chance that you might have to spend a little bit of extra time in multiprocessing. Then we talk about multi-threading, which 111 talks about in like the first week or two. So you will definitely be fine there. And then we spend some time talking about networking, but it's going to be not a whole lot of prereqs for that material. So I think you'll be okay, but I can't promise anything. The class is pass-fail. Like as long as you try, we don't anticipate failing anyone. If you don't turn anything in, then you don't really give us a lot of choice. But if you're trying in the class and you're turning stuff in, you're going to be fine. But that being said, you'll get out what you put in. It will like be totally possible to pass this class without putting in a lot of time. But I think you'll get a lot more out of it, and you'll learn a lot more if you are able to put some more time in. The components, there's weekly exercises, which should take like 1 to 4 hours a week. There's 2 projects, which will take a little bit more time, but they're spread out over more time, so you'll have more time to finish them. And then participation, just like coming to lecture, asking questions. Again, we want this to be a chill and fun class for you. So as long as you put some time in, we'll be fine. There are 2 projects, like I mentioned. So the first project will be a mini implementation of GDB. You'll implement your own debugger and see how a debugger actually works. And the second project will be a high-performance web server. So you'll notice these are not like security projects. This is not a security class. It's more so like how do we write good code. So you'll take the lessons from this class on how to write good code, and then you'll build a practical project using those lessons. Yeah, okay. So, so for the projects, if at any point, again, we want this to be a fun class for you. If you don't like these project ideas, then we would love to chat about what some of your other interests are. For example, if you're interested in computer graphics, maybe you can implement like a high performance ray tracer. But we're super flexible, and so if you have another project idea, feel free to propose it. Some people last year proposed like building a thing that shows how the Rust analyzer or how the Rust compiler analyzes your code and showing out like what's going on inside of the compiler. And I thought that was a really cool idea. We have weekly exercises. You can substitute any exercise for a blog post. So if you are like, oh, I'm learning this thing, it's kind of cool, let me write about it, or oh, I'm learning this thing, this is super frustrating, I don't understand this at all, like why did they make it like this? I think it'd be really good for you for your learning, and also good for you professionally if you write about what you're learning and your experiences and frustrations and everything, and publish that. So if at any point you're interested in that, just let us know. Nobody took me up on that last year, but I would love to see that happen. Okay, so there's a short code snippet linked here on the course website. It is an implementation of a vector in C. So this is kind of like maybe going to bring back bad memories from 107. But this code has at least 7 bugs relating to memory. It's really broken. There's a lot of things wrong here. If you just take 10 minutes to look at it briefly and try to find as many problems as you can, like don't spend a lot of time on this. You don't have to find all of them. But we may, I'm not 100% sure if we'll get time to talk about this on Thursday, but we might get to it at the end. And if not, then we'll talk about it next Tuesday. So if you have a chance, give this a look. Don't stress about it, but that is up on the course website. Any other questions? Anything I can answer? Any logistics questions or questions about material we talked about? Also for office hours, I will always hang around after class, and Julio will have office hours after class on Thursday. But if you want to chat with us and those times don't work for you, then please message us on Slack, and we would love to set up another time. And again, if you haven't gotten a chance yet, make sure that you get on Slack, post an intro in the social channel, and fill out the Google form that I emailed out. If you have any questions about that, any of that, or it doesn't work, please let me know. Awesome. Well, thank you so much for coming, and we will see you on Thursday. Have a great week.